Hello and very big welcome to everyone that is joining in. This is a webinar that is hosted by Brief Battery Technologies, and the topic we're going to cover today is how simulation helps battery teams or organizations that work with batteries in development programs, how they can make durability decisions sooner. My name is Oskar Nordlander. I work as a product manager here at Brief. I have a past experience working as a battery simulation engineer, but also a battery validation engineer, focusing mainly on durability topics, especially in swelling force estimations. And I'm also joined here today with Jishnu. Jishnu, maybe you can introduce yourself as well.
Thanks, Oskar. Hello, everyone. My name is Jishnu Ayyangatu. I'm one of the battery model developer here at Breathe, mostly focusing on development, parameterization, and validation of physics-based models with a specific focus on degradation modeling. I've been with Breathe for about a year now, and before that, I was doing my PhD at University of Warwick. Quite excited to be here.
Right. Me and Jishnu, we envision that this presentation will be around 30 minutes in total. And thereafter, we will open up to Q&A session as well, where Jishnu and I will answer some questions if you have any. So if you have any questions that pops up throughout this presentation, please list them or write them down, and then we will answer them afterwards as well. So for the context of this webinar, we have split it up into 3 different segments. The first one is that we will start by going through the challenges of durability testing in cell development programs, and also looking deeper into why decisions are hard to make early in development programs. Thereafter, Jishnu will take the lead to run us through how a validated degradation model is built, but also tested and also used. Thereafter, we will also look at the approach, how simulation can help focus aging test programs and what you can use it to do and improve on optimal test design. But also we will show you how you can prove the value we're presenting today on your own battery cell and your own data that you have from your test campaigns. And last but not least, we will also go through a path forward. We will show you how we construct a proof of concept with our degradation capabilities at Brief. And then also, as a last remark, you will also get access to a free performance trial that we have for our product Brief Simulate in the end for a commercially available cell, where you can try out all the different features and functionalities that we have to help you enable to do battery development better, but also put battery cells on the market faster. To start off with the challenge, I think as many of us, or not, probably every one of us, know that we are testing a lot in the battery industry, and we construct these testing campaign, or we can phrase it almost as a validation campaign as well, across multiple temperatures, multiple SOC windows or DoD windows, and also current values. And these campaigns are often one of the time-limiting factors in development programs. And depending, of course, of the application that the cell will be subjected to, these programs can run for several months, even not years, depending on what chemistry and application field you're looking into. And what we hear from the industry is that key decisions that needs to be made on a strategic level for the end product needs to be made before evidence from these test campaigns arrives, meaning that control strategy, system architecture might already be locked in before you actually know how the cell will perform down the road when it has degraded in the test setting. Looking also from maybe not from a technical perspective, but more from an organizational perspective, I think it's also very important to acknowledge that testing is incredibly expensive as well today. And for a validation campaign in the industry, it can be subjected to hundreds of cells that needs to run in parallel also. So it's also not from a timeline perspective, but also a cost perspective that this test campaign is also very expensive to run. And lastly, as well, I think it's also very important to realize, are we actually testing the right things? A lot of intuition and knowledge are being used actually to set up these test matrices to some degree, but without the degradation model that are accurately able to show the aging modes, but also the aging mechanism, we don't know for certain with physical evidence if we're testing the right things. Zooming out from maybe a setting of a laboratory or a test chamber setting as well, there is also a real use case applicability in the end. All of these battery cells that go through development will, at a certain given time, start the production and also go into vehicles, go into phones, tablets, and so on. And we have tried to paint up an example here of what you can almost phrase as an automotive challenge. In the end, every single vehicle is delivered with a set warranty and performance figures, but in the real world scenario, every single car will be subjected to different environments, climates, but also an end user. And in this scenario, we have 3 different personas. We have, for instance, Anna here on the left, that is a sales professional that lives very far up in the Arctic in Sweden. She needs to drive long distances every weekday. And what matters to her is that she can have confidence that the vehicle actually has the range that it needs, but also that she can rely on the car actually have reliability during winter periods when it can reach -30 degrees. Lucas, on the other hand, he's a director that lives in Central Europe in Munich. He drives on the Autobahn every single weekday, high speeds, but also fast charging the car every single weekday as well. And what matters to him is completely different in relation to Anna. He wants fast charging speed, but also he's keen to have performance retention as well of the vehicle. And then last but not least, we have David. David is retired, but he lives in a really hot climate that it is in Arizona. He does some occasional weekend trips, but what matters to him is the longevity and also the second-hand value of the vehicle. And in the industry today, a lot of these use cases that spans over hundreds of thousands, if not million, becomes a blind spot. And often the performance metrics and the durability metrics are made on the harshest scenario. This is something that we want to change at Brief with our physics-based degradation approach, where we can fundamentally simulate and also predict every single use case, so no market becomes a blind spot for our customers. And this also then applies on consumer electronics and other sectors as well, not only automotive, that this example highlights. And when we speak about decision confidence and also, I guess on an organizational level, what direction you're taking, I think the industry are not short of running any test. We're doing more tests than we actually probably should be doing, at least what we hear. But the question becomes, are we actually running the right test? Are there any blind spots that we should be testing? Are there any crucial performance metrics we should look perhaps at low temperature? Should we look at the specific DoD interval? But also with the physics-based degradation model, as we stated earlier, the decisions arrive too late. Maybe you have a design freeze that is coming up, but perhaps you haven't made through enough state of health of the battery to actually ensure that it performs below 90% state of health. This is something that we want to equip our users and clients with, so they can actually act on confidence before any critical milestones need to be met. And in terms of the visibility on the durability aspects, what we have so far been able to identify is 3 separate buckets that we will cover today. And the first bucket is what we covered with the use case scenario, is that organization often design for the harshest case as a fallback method. This then leads to performance might be constrained, based that everything is based on the worst case assumption. Maybe you have an excess cooling strategy that is not needed, perhaps for 95% of the end consumers. The second bucket we will look into is the broad aging matrices. This is also as a fallback mechanism when teams need to figure out a specific scenario, let's say. The fallback method there is actually to test it and run an additional test campaign that might be running for perhaps a couple of months, maybe up to several years as well. But also lastly, looking at the warranty risk. looking at the exposure or different geographical settings, use case scenarios, and so on, and looking at that the end product have the same warranty, but the product as it is will have very different aging paths also. With that said, I will leave over to Jishnu that will guide into more technical depth of the degradation model.
Thanks, Oskar. So Oskar has nicely painted out the 3 technical challenges that industry face when it comes to degradation. In the next few subsequent slides, I would show how having access to a physics-based degradation model that is well parameterized and validated, in addition to your testing data, would help alleviate some of these challenges. So to start with, I would like to explain how the model is constructed here at Breathe, then what value it offers. So in this slide, the first 2 rows that deals with how the model is constructed, and the last row here that explains the value. So let's look at the first 2 rows. The first row correspond to how a electrochemical performance model is built here at Breathe. That would then lay the foundation to build a degradation model on top of it. And that is explained in the stage number 2 or track number 2 here. Looking at it a bit more closer, so the track number 1, the idea is the customer send us a few number of cells. We do an extensive test campaign on it. This could include a wide variety of tests, including half cell 3 electrode measurements, SEM images, etc., and also a lot of full cell tests, including TCI test, WLTP, constant current experiments, etc. Using this array of experiments that we have collected, we then parameterize and validate an SPME type electrochemical model. This entire exercise, that's a track 1, that would take about 6 to 8 weeks upon delivery of the cells. And after this, the customer would receive this beginning of life performance model with which they can run any electrochemical or thermal simulations of their choice. So after that, we enter the track number 2 or stage number 2, where the degradation model development happens. Here, we take this electrochemical model as the foundation and add submodels that describe dominant degradation mechanisms. The key input here is aging data, which either the customer can provide or we do in-house testing here at Breathe, our London-based lab, for an additional charge. The first stage then is we analyze this aging data using techniques like degradation mode quantification, etc., to understand what the dominant degradation mechanisms are. Only then we start with our model development. Based on this analysis, the degradation mechanisms that we identify, we translate those. We use differential equation-based submodels for those degradation mechanisms and couple it with the electrochemical model that we originally created from the stage number 1. So that would be then our degradation model, which is not just a degradation model in the same sense as of an empirical model. This is an electrochemical model coupled with a degradation model. So you get both performance at any stages of aging as well as the degradation trajectory. We then do the calibration and validation of that model based on the aging data and ship the model in about 4 weeks, after which we have the degradation data available. Good. So at the end of stage 1 and 2, what we get is this coupled electrochemical degradation model. And the value of such a model is quite simple. It can act as a virtual battery. So any aging test that you might run on a physical cell, the same test can virtually be run on this degradation model now at virtually no cost. The advantages then would be a customer can easily incorporate this into a system level simulations, let's say, and run simulations to make informed choices on the design parameter of the system, design parameters at system level. This would be a more optimal, more engineering-based approach rather than putting a large safety net and when we don't have any information on the degradation under the use cases under which the system would be used. Similarly, having access to this degradation model, it can then help design a more optimal test metrics for any subsequent test that the customer might do on the same cell or any new cell samples along that manufacturing line. Also, linking back to one of the key points Oskar mentioned a few slides before, this each cell would undergo different degradation paths under different use cases. And the advantage of having this electrochemical degradation model is we can not just simulate the standard constant current or current rating, we can also simulate under different mission profiles. And this would then help OEMs set warranty based on the specific use case of the battery rather than going with the worst case proxy. Cool. So essentially what this slide shows is, okay, how we develop the model and what the value of having this model is. But this value, all of this would be only useful if the model can actually predict how the real life battery would degrade under the same condition. And that's where validation comes. So here at Breathe, as I previously hinted, we use only a subset of the total experiments for model calibration and then do held out validation on the rest of the condition which were unseen during the calibration phase. For example, you can, in the figures here, you can see SOH capacity, SOH based on capacity, trajectory, and a few calibration condition and a few more validation condition on the right-hand side. For all the batteries that we have tested so far, we were able to get plus or minus 2% accuracy on the SOH across all the experimental conditions, both calibration and validation. So that definitely gives confidence in the reliability of the model. But we here at Breathe, we recognize that that's not enough, because different internal aging pathways within a cell can give rise to the same capacity trajectory. So just getting an agreement on the capacity trajectory is no indication that we have actually captured the right aging pathways. And that's quite important, because if we test this model under a different experimental condition, if we don't get the aging pathways right, the validation might be poor. So to ensure that, here we extend our validation to include also other aging indicators. So essentially, the more aging indicators that we get agreement upon based on, like if the model agrees with experiment, that means there is more and more confidence that we capture the right aging pathways. So to do that, we extend our validation from just the SOH metric to also include DCIR and 3 degradation modes. So that we have loss of lithium inventory, loss of active material on the negative electrode and positive electrode. So in this graph, each column corresponds to a particular SOH indicator, one of the 5 that I mentioned now. The y-axis here shows RMSE in terms of percentage. Each of the data point here correspond to a particular aging condition. Now, this could be, here we have about 10 cyclic aging condition and 10 calendar aging condition. So here the cyclic aging conditions that we use goes anywhere between 0 to 45 degrees Celsius and current rates of 0 to 3C and different depth of discharge windows and voltage windows. Similarly, the calendar aging here, it was done for about, I guess, 2 years window, and it was done at different storage temperature and SOC combinations. Now, as you can see here, this includes both results from calibration and validation, and across all the data sets that we have considered and across all 5 aging indicators, we were getting very good accuracy, and the RMSE is less than within the 2% threshold I mentioned in the previous slide. So this gives much more understanding of the reliability of the model, and that gives us confidence in what it predicts for like a totally different condition, which is how the model would then be used. This slide here essentially shows the same point. Here we show for one of the validation condition here that is corresponding to one of this data point that is shown here. Here we show the capacity, capacity source trajectory, lithium loss trajectory, and active material loss of negative electrode from the model plotted against experiment. And here we are getting very good fits. So just extending the point that I mentioned on the previous slide. So taking a step back, what we showed now is the reliability of the model is heavily based on how well it is validated. Here at Breathe, we do held out validation, not just on capacity SOH, but also on other aging indicators. Cool. Then we go one more step ahead of this. That's instead of just validating on the SOH indicators, we also validate on the electrochemical performance at different stages of aging. So one of the key advantages of having this coupled electrochemical and degradation model is you don't just get the average degradation trajectory, you would also get how the electrochemical behavior evolved at different stages of aging. So one of the examples here is, here we have C/3 charge and discharge from the model. So the model prediction plotted against experimental data. The gray one here is the model prediction, and the green one here is experimental data. And we get very good agreement at the beginning of life. So this is just our electrochemical model. But then the degradation model tells it, okay, how to change its internal settings so that we would get good voltage validation accuracy also at different stages of aging. So here again at SOH equal to 88.7, or like after end of life 79.3, we are getting very good accuracy, not just on SOH, but also on the electrochemical performance. So this then would be quite useful to the customer. Instead of using an empirical model here, the insights that you get is much more richer, because you don't just get degradation path, you also get how the performance changes with aging. We give some auxiliary tools with it to make full use of this. For example, the user get tools to create the equivalent circuit model parameters at any given stages of aging, so that they can easily incorporate that into the system level simulations and check, okay, going back to the original point, to design parameter optimization, or like to simulate how emission profile would look like at a given stage of aging, things like that, or tune the controller setting, etc. So yeah, that's it from me. Thank you for indulging, and yeah, back to you, Oskar.
Oh, thank you very much, Jishnu. Thank you very much. I will take a moment to zoom out a little bit and also reflect on what Jishnu just ran through in terms of the subset calibration that we run with our degradation approach, but also linking back to the problems with the decision making in the industry today. Here we have listed out similar kind of numbers that we looked at before. Usually a validation campaign or test campaign consists of hundreds of cells. We have 200 as an example here. For us as a company brief, if we would run this validation campaign in-house for 18 months, it would be roughly at a cost of £3 million to have the fully experimental approach. But with our degradation model and the capabilities and the accuracy it has that Jishnu showcased, we are comfortable enough to state that we can reduce the amount of allocation of tests in our channels, but being between 30 to 50%. So in looking at the aspects of running 200 cells experimentally, we could reduce that number to in between 100 to 140 cells. The reason why this is a span and not a fixed absolute value is because every single organization is running a different, or I would even phrase it as a tailored test campaign. They're interested in different things, and therefore we have an interval that we are confident to state. In terms of cost perspective as well, in this example, it would account to a cost saving of around £1.5 million to £0.9 million. But the cost and time metrics aside, from an engineering point of view, at least in terms of return of investment, it allows engineers to actually use the model not only to replace tests with the simulation-driven workflow, but it provides engineering value in the aspect of the model can be used actually to do more informed, optimal test design for future test campaigns as well. The model can be used to evaluate different aging mechanisms and aging modes as well, to actually find out where these experimental resources should be put in order to get as much information as possible how the cell performs, both from a performance perspective but also from a durability perspective. But also it provides you with the predictive insights as well that the first day you receive it. So coming back to what Jishnu said, being a physics-based model, it allows you to not be in the frigid or rigid approach as a statistical or an empirical approach has. You're able to simulate your use cases, even use fleet data for that matter for your products, but also evaluate control strategies and warranty quantification as well throughout life to see how, let's say, a fast charge protocol, for instance, would change. And going forward and looking at how we go about actually working with clients on this from a proof of concept point of view, is that the first step of the process is that we are working with our clients and collaborating and looking at their test matrix, and also hearing what actually matters for that client. As we both, Jishnu and I, stated earlier, there's no set in stone test matrix that everyone is running. it varies quite a lot depending on the industry you're working in, but also what kind of cell chemistry you're working with. So we are collaborating with our clients and looking at what these potential calibration test protocols would be. And thereafter, we provide insights in which test protocols can be reduced by the degradation model. The next step after that is that we calibrate the degradation model based on the subset protocols. And the third step then as well as an important with every single model is then that we validate the model based on unseen data that the model hasn't seen before. So looking at the aging modes and the SOH trajectory, but also the voltage response to ensure that the model is performing according to the success metrics as well. And then the last, but absolutely not least, and I also would see it as the most fun process as well, that the customer then receives the model, where you can do your use case studies, looking at control strategies. And the format that our degradation model is delivered today is in the main interface as a Python API, but we also support then export alternatives into MATLAB or MathWorks environment if that's your more preferred environment to work in your organization. And a complete timeline going through step 1 to 4 on this slide is a process that takes weeks and not months. So the workflow that Jishnu presented from a performance model all the way to have a ready-to-go degradation model is a process in between 10 to 12 weeks for us to construct, but also validate and deliver to our clients. Physics-based model has been very much a research object for quite some time now as well, and is often seen as the real value for physics-based model lies for the simulation engineer or battery modeling engineer. But the value of having this kind of capability and tools available spreads across the whole organization. We have talked a lot for the persona of the battery engineer today, looking at that allows that engineer to predict aging earlier than it has been before, but also being confident that the model is constructed and validated on physics and not simple curve fits that empirical approaches are. But it also provides insights for the battery engineer to actually focus the resources on what matters, and being able to actually find out which tests are the critical ones that I need to run for my next test campaign as well, to ensure that the battery is performing the way that we anticipated to do. On the other hand, a systems engineer is benefiting from this kind of capabilities, and of course in a little bit different way. But from a scenario, it allows the systems engineer to run different control strategies, not based on beginning of life scenarios as it usually is, but actually have an aging aware dependent SOX estimator, let's say. Can also run control strategies with different annual potential threshold throughout life and see how that affects the whole platform in different climates, let's say. And we have also, with the wide variety of different engineers in organization, that's also one of the key reasons why we supply the degradation model in multiple interfaces as well, or tech stack environments, such as Python, but also MATLAB, Simscape, and Simulink. And also from more of a commercial and program point of view as well, in terms of the decision making, a physics-based or physics-aware degradation model allows you to make decisions with evidence months earlier and not base it on intuition or past knowledge. But you will also be able to see real cost reduction as well, that testing can be replaced by simulation-driven software. But then also being able to quantify the warranty exposure as well and find where you might have a blind spot or something that you need to revise on the warranty side. So it allows you to cover as many use cases as you might have, but also fleet data for that matter. So to round off, what we see it as is that battery teams or organization that understands degradation are also the ones that can act earlier with confidence, meaning that they can put products on the market faster than anyone else. I think it's also aware to mention as well as a remark is that degradation is context dependent. A model that is able to accurately represent a use case or a very, very large variety of use cases is more powerful than a single use case or a single experimental test in the lab. But also, secondly, is also that the validation of this kind of tool is also very important. So it lets you focus on what matters. But being very accurate and being able to provide you with evidence also allows you to actually move these kind of milestone gates forward by months. And when we are also able to prove this today with your cell, with your application that you're using it in, with your data as well, within a couple of weeks and not months or even years for that matter. Also, as a last, before we jump to the Q&A now, as well, I think we have a free trial, as I mentioned earlier, or at the beginning of the presentation. I think there's a link on the top right. If you have the tab open as well, you can press that link and it will redirect you to our sign up to receive a free instance of a Molecell P45B cell that we have available in Brief Simulate. We haven't gated any kind of features or functionalities in the product for trial users, so you will be able to use anything that a paid customer would be able to do for this cell. The only thing that is not there in the free trial is degradation availability. But if you're keen to have a deeper look or deep dive on degradation and how we can bring it to your organization, feel free to reach out to us and we can set up a follow-up call session as well, or even workshop to go deeper into the subject. With that said, I think we can jump into the Q&A now. Jishnu, do you have a view of the Q&A?
Yes, I can share some of the questions here to the stage. Cool. So this is a question from Sam. How do we get experimental measures for the degradation modes? So to get the degradation modes, which are LLI, LAM on both electrodes, what we do is a technique called degradation mode quantification. So the idea here is we use half cell OCV measurements for both electrodes and construct the full cell OCV from that. When we are doing this process, what we are optimizing for are the stoichiometric limits at both full cell and fully depleted cell. So like what are the stoichiometry values of anode and cathode at a fully charged full cell and fully depleted full cell. We do this at different stages of aging. If we get POCV data from the full cell testing at different stages of aging, and we get the stoichiometric values at different stages of aging. From that, we can calculate what is the total number of lithium that is available in the cell now, and what is the capacity of individual electrode, which we then compare against the beginning of life values to get the degradation modes.
Right.
Cool. So another question from, I guess, this is from Claire, and the question is, what are the degradation mechanisms that we consider in the model? So we don't, like, there are no fixed number of degradation mechanisms that we would include in the model always. We make this decision based on the aging data. So the first stage of our model development, before constructing any of the differential equation, we first look at the aging data, do analysis, including the degradation mode quantification to understand, look at SOS trajectory under different use cases, look at degradation mode trajectory under different use case, and then try to understand what are the dominant degradation mechanisms that are present in the cell. So that would be our first starting point. And from there, like, we then create the model by incorporating differential equations of those dominant degradation mechanisms into the model. So TLDR, we don't have fixed mechanisms. We make it adaptive. We first look at the data and decide that. Cool. There's another question from Dr. J. Santoki, and the question is, what are the minimum number of data set needed to initiate the model development, and how many tests are generally required before the model achieves about 95% predictive confidence? Thanks. So this totally depends upon the degradation the use case of the degradation model. So the number of experiments needed for calibration would depend upon the operational envelope. That is, like, what are the temperature range that you want to consider, what are the C rate range that you want to consider, and like the SOC windows, etc. And also depend upon cell chemistry. If there is silicon present in the cell, then yeah, we would need some additional tests for that. So there's no definite answer, but for the use case that was shown in the previous slide, for that we used about 7 cyclic aging conditions and 3 calendar aging conditions to do the model calibration. Cool. There's another question from Emily Thorne. Given the model runs at an electrochemical timescale, how practical is it to simulate a full aging experiment? Are we talking about minutes, hours? So, okay, you're right. The model simulates at an electrochemical timescale. That's the fastest process in the entire model, and then we let it simulate for, like, okay, how many number of cycles that we are simulating. The best speed that we could achieve for constant current experiments consistently, we are able to say, run about 100 cycles in 1 minute. And for calendar aging, it is even more faster, but if it is a drive cycle, it might take a bit longer. Cool. Then another question from Tosh. Thanks, Oskar and Jishnu, for great insights. I have 2 questions. What are the degradation models that are used? So we answered that already. So we don't go with prescribed degradation mechanisms. We make it adaptive. We look at the aging data and make that decision. What do we do in cases where the degradation mechanisms dominating are not one of the classical ones? Example, current collected delamination. Very good question. So, of course, you're right. At the starting point, after analyzing the aging data, if we get insights that there is a degradation mechanisms that we are not aware of at that point, the best way to proceed is, okay, this is scientific information that we don't know. So the best case then would be incorporate a phenomenological model to capture that bit of the degradation. So the total model would be an electrochemical baseline that is fully physics based. There would be multiple degradation mechanisms. Let's say there are 5 and we have physics known for 4 of them. So we incorporate the physics-based differential equations for those 4, and the last piece we replace that with a phenomenological model instead of going with a physics-based model. So that makes it a bit so. Degradation, of course, is a very challenging problem, and there aren't answers for all the degradation mechanisms even available in literature, even in academic literature. So this is the most pragmatic way we thought of going about it. Cool. So that's...
I think I found a question here, Jishnu, as well, that we get asked quite a lot as well, but I think Sylvian posted it here on the Q&A as well. Are we able to predict sudden death?
Yeah, very good question. So this is one of the drawback of the model in a sense, and something we are actively trying to improve. So the sudden death or knee effect of a battery could be, there are multiple causes that could lead to the knee effect of a battery. So there are some mechanisms that we have captured in our model that would explain the knee effect, but there could be a lot more, because this could be like something that are inactive throughout the entire phase of aging, which wouldn't get picked up during the calibration data, and something like it crosses a threshold and all of a sudden, like, yeah, the cell goes through a very accelerated degradation path. But that's something even academic literature don't have the answer for, and would be one of the areas that we are actively trying to improve.
Yeah, and I think also to add on this is that with all software or models aside as well, we also think, and I would like to emphasize as well, testing is good, right? And this is one of the reasons why testing is good, to actually have some confidence, especially on sudden death or knee point also. So in terms of validation and testing campaign, testing is good, but it's a matter, I guess, a question of which test should be running until the sudden death or to the knee point is the key thing here.
Cool. I think that's all the questions.
I think we have one from Chad that was just posted now, I believe, as well, if you don't mind.
Okay, yeah, absolutely. Cool. Have standard performance tests been validated late in cycle life? Example, 10C C/5 to 10C discharge, both from voltage response and overall cell heating. Also, other tests such as HPPC. So, at the moment, all of this validation, like we do an extensive electrochemical validation at beginning of life, and at a later phases, like we only validate across some of the CC datasets that we have. So, this for the aging study shown before, we validated on voltage response of C/3 and 1C. We don't do an extensive validation at later phase. This is something that can be done. The reason we don't do it now is since the electrochemical model is already validated at beginning of life, what changes in that model are some of the parameters internally. We get proper validation of that by looking at the SOH trajectory as well as some of this voltage validation that we already do. But of course, this is possible, but yeah, something we don't do now. Cool.
I think that was the last question as well.
Yeah.
And if any questions comes up afterwards, or if you're looking at this webinar as a recorded session, feel free to reach out to us at Brief as well, both me and Jishnu, or send a message or an email to our hello address, and then we will make sure that your question gets answered as well. But with that said, we want to thank you so much for attending this webinar and taking your time to listen on this very big topic of degradation as well. I wish you all a very nice Wednesday, wherever you are in the world as well. Might be evening, afternoon, or morning. Okay, thank you so much, everyone.
Cool. Thank you, everyone.
Thank you. Bye-bye.